go ahead.
So this was in third lecture, ENBS plots that we made. So I don't know, I think there's a circular argument or something that I can't understand. So for the reversible path that you're using, you say that because it's adiabatically reversible, SA is less than equal to SP or SP is less than equal to SA, you get the mean.
Yeah.
And then for the pattern, you take BU and you say SU greater than SP greater than SP.
Yeah.
But I don't see a reason why entropy should be, or that function, as call it whatever you will, should have an increasing value in NB and E. I mean, for all practical purposes, I could have a lesser than sign also, it would still hold. Like you're using a part of the postulate to sort of show.
Sure, this is not a proof. The point here is that there is something which you can learn just by looking at this picture, just by looking at the location of the states. There is something you can learn which tells you whether a process is possible or not.
Right.
And yeah, you could have had some other function. In the end, entropy maximization is equivalent to energy minimization. So what you're saying would have led to an energy principle.
But my question is that you could technically have that SND being any form of volume energy in the number.
Sure.
So why do we assume it's one that gives me this particular behavior that increases from?
No, we are not assuming that. We are saying.
So the constant volume process, you're saying it's.
What we are saying is for this process, since we can go back and forth in any direction, while for this process, we can go only up. So it means as if this point and this point are accessible from each other adiabatically, while the red point and the blue point are accessible only in one direction. This we are using to derive intuition. This is not a proof. So if you want to get stuck in the proof land, you will get stuck for sure.
I get that. I'm saying I understand that here it's the parallel, you can't give energy back to the thing.
Yeah.
But I could have those signs flipped, right?
Absolutely.
Right.
Absolutely. But this is not about that. This is about there existing a function which has this, just by looking at the state, you can say whether it is accessible or not, right? So instead of S, I would have defined minus S.
Okay.
No one's stopping me, right? That's the whole point. This is showing us that things are accessible or not can be defined only by looking at the thing. Okay. By the way, you can come to my office and ask me questions. I cannot guarantee whether I will respond to you or not. I might look kind of pissed sometimes if I'm thinking about something. Does not mean I don't like you, like it happened to him. So you're welcome to come, but I might just say I don't have time right now. Same, but that's why Slack is better. You know, you can always message me on Slack. Yeah.
One more thing that the last part of the previous lecture, you wrote the partial derivative first as del S del, and then you, to be more rigorous, you wrote that 1 over del S by del E.
Yeah. No, I don't think 1 over del S by del E was needed. Someone was trying to trip me. That is Omar. He was trying to trip me. I don't think it was needed.
I'm wondering, is that because you're working in one representation?
Yeah, and we stayed in that representation. Okay. There was no issue there. So let's start with something we mentioned last time, and then we will start from there. So last time we said that the heat given if a process is happening reversibly, which is very, very slowly, you're staying in equilibrium, not the same as adiabatic, is equal to T times ds, right? How did we derive this? In order to derive this, how did we do this? In order to do this, we wrote down TE is equal to TDS minus PdV plus mu dn. And then we wrote down DE is equal to TDS. Sorry, DE is equal to delta Q reversible minus PdV plus summation mu dn, right? We wrote something like this and we compared these two term by term and we said, therefore, these two must be equal to equal. That was the idea. So we got delta Q reversible equal to TDS. What about delta Q adiabatic and reversible? what is going to be the value of this one? Why?
Because
It's adiabatic. Adiabatic means no heat transfer, right? So it's going to be 0. How about delta Q, adiabatic, irreversible? That's also going to be 0. It doesn't matter whether an adiabatic process is happening reversibly or irreversibly. Heat change is 0. How about delta Q, irreversible in general? Do we know anything about that? What could it be? Later we will see, we haven't studied this yet, but later we will see that this is actually less than equal to TdS. We will see this after few classes. Okay. And everything else just comes out of this. Because we have an equal to sign, you will see that all the other things fall out of this. This is known as Clausius inequality. And we will be doing this later. But for now, we have definitely seen that delta Q reversible is equal to TdS, and delta Q adiabatic doesn't matter whether it's reversible or irreversible, is equal to 0. Yeah.
And what equation you have less or equal?
Less than equal.
Equation you have equal.
Yeah. Yeah. The first one is equal, while this is, it's my elephant less than equal to. This is less than equal to. Okay. Well, the equality holds only for reversible.
I'm confused by the case when in what there is a situation, possible situations.
Sure. So when I say irreversible, what I really mean is real. A real process can be an irreversible process which is being carried out infinitely slowly. Reversible process is a limit of irreversible process, right? So irreversible process, the terminology sounds confusing, but it's a superset. Reversible is, so I think this is the world of irreversible processes, and somewhere in this corner there is a little dot which is a reversible process, or maybe here, the limit. Okay. Any more questions?
you can't actually have a reversible process.
You can.
Like theoretically, yes, but
Yeah. Well, time is increasing, right? So we are screwed anyway. We're all dying. Then that's the one thing I need you to remember. The other thing that we looked is we thought about energy is equal to energy as a function of SVN, and I introduced the term natural variables. Alex asked me what's natural about them. I said they are not unnatural. I did not really give an answer. We will see why they are natural variables. And in this representation, we wrote down that dE is equal to partial E by partial S, keeping NV constant, plus partial E by partial V, keeping S n constant, plus partial E by partial N, keeping SV constant.
Units.
Huh?
Left and right units are very different. I think if I don't.
Oh yeah, I was going to write this. Happy now? Good. And then we said, so this is known as the fundamental equation, right? We have seen two fundamental equations so far. We saw E as a function of SVN. Similarly, we had S as a function of NVE. That's also a fundamental equation, and they carry the same information. Why do they carry the same information? Because E and S are monotonic, keeping everything else constant, right? So there is nothing new. You can write any of these equations. And from differentiating this, we get this equation. This is a fundamental equation, either of this. Here we introduce terms, temperature, which is partial E by partial S at constant NV. Now that's going to be a function of what? This will not change. The representation, we are working in the energy representation, right? So this is still going to be a function of S and V, okay? Similarly, we introduce P, which is minus partial E by partial V at constant S and N. This is also a function of S and V or SVN, whatever you want. The order does not matter there. And mu which is partial E by partial N at constant S comma V is equal to mu, also a function of S and V. Okay, this is simple but kind of subtle. You think like, well, we have removed it, it should be a function of something else now, but no. It is always a function of S and V, the three things that you see in the ground floor, okay? And while this was a fundamental equation, these three are known as equations of state. Okay, so these are known as equations of state. I was careful with my numbering. I'm going to call it equation number 4a, equation number 4b, and I'm keeping the equation numbering consisting from class across class. Once in a while I will refer, so when you study, you can go and look back at things. So turns out knowledge of one equation of state or even two equations of state does not give us the fundamental equation. However, knowing the fundamental equation, we can go back to equation of state. The second part is trivial, right? The equation of state is literally the partial derivative of the fundamental equation, right? So if you know the fundamental equation, you just go and differentiate it and you get any equation of state that you want. Why is it not possible to go from one equation of state or two equation of state to the fundamental equation? Someone who has not answered yet. Nathan, what do you think?
Well, you're missing information, right? Making an equation.
What information are you missing?
So if you use DE, if you're given just T, then you're missing DE, DN, and DN.
Yes, you're missing. It's a function of three variables, and essentially, it's almost like knowing the derivative and trying to estimate the function itself, right? You can't just integrate and go back. There will be some undetermined coefficients and things like that. Okay. However, if we knew all three equations of state, that can go back to fundamental equation. And we will show how exactly to do that. Okay, if we knew three equations of state, how do we go to the fundamental equation? So in order to understand this, how do we go from three equations of state to fundamental equation? We are going to look at something which you have probably studied in math, known as Euler equation. If you have forgotten what's Euler equation, that's totally fine. No need to panic. We will derive it here. And it's quite simple. So in order to prove, let's prove that three equations of state, knowledge of all three equations of state, indeed gave us fundamental equation. How do we do that? So let's work in energy representation, where we have E is equal to E of S, V, N. So E is extensive, right? This was our starting point. So if E is extensive, what can we say about E of lambda S, comma lambda V, comma lambda N? It's going to be lambda multiplied by E of SVN, right? Let's differentiate the above one with respect to lambda, both sides, okay? So what do we get? We get partial E by partial lambda S multiplied by partial lambda S by partial lambda plus partial E by partial lambda V multiplied by partial lambda V by partial lambda plus partial E by partial lambda N multiplied by partial lambda N by partial lambda. And I'm not writing down in the partials what is being held constant, just being a bit lazy, is going to be E of SVN multiplied by partial lambda by partial lambda. Okay, so what do we get this side? We get partial E by partial lambda S, and this thing becomes S, right? Plus partial E by partial lambda V, and this thing becomes V. Similarly, this thing becomes N. Partial E by partial lambda N is equal to, what do we have here? Just E of SVN multiplied by 1, right? Partial lambda by partial lambda. So what did we get? Before we say what did we get, now let's put the value of lambda equal to 1. So this derivation is almost a bit like magic every time I see it. Let's put lambda equal to 1. Then we get partial E by partial S multiplied by S plus partial E by partial V multiplied by V plus partial E by partial N multiplied by N is equal to E. We have seen these things before. What is this one? T. In other words, E is equal to TS. What is this one? Minus P. Don't forget the minus sign. Life will become very painful. And what is the last one? Chemical potential, right? And here I have done it for one component system. You could do it for multiple component system, or you could just imagine there are Einstein summations there, and it is already for multiple component systems. So we just derived an interesting equation, which looks almost like what we wrote for dE is equal to TdS minus PdV, but it is a bit different. So this equation, which I'm going to call equation 9a, why did 9 suddenly come from? Because last time I stopped at 8. Is known as Euler's equation. Euler didn't do it in thermodynamics. Euler wasn't really thinking much about thermodynamics, I think, but it's just a property of homogeneous first order functions, which you have seen in calculus. You can also write it down equivalently. If you take TS on the left, if you take everything on the right side and only keep TS on the left side, you will get S is equal to 1 by T E plus P by T V minus mu by T N. This we are going to call equation 9b. So S is equal to 1 by T E plus, yeah, okay. So these two are both are known as Euler's equation. So now do we see how would we go from knowledge of all three equations of state to the fundamental equation? What would we have to do? So if we knew all three equations of state, what do I mean by that? I mean, if we knew T is equal to T as a function of SVN, P is equal to P as a function of SVN, and mu as a function of SVN, we could put all three in Euler equation. E is equal to T multiplied by S minus P multiplied by V plus mu multiplied by N, right? So this one would go over here and you would get a function of SVN, right? Because you know T as a function of SVN. This, oh, didn't mean to erase. This one will go over here. And again, you get a function of SVN. This one will go over here. And again, you get a function of SVN. So knowing all three equations of state and putting them in Euler's equation, you recover the fundamental equation. Okay. We would have E as a function of SVN. Notice that Euler equation on its own is not a fundamental equation. Why? So what's wrong with just this being a fundamental equation?
One is unknown, then you cannot get.
Sure, but that is true. But what I was trying to say here is that this is not just a function of SVN. It is a function of some other things also. Which things? It's a function of partial derivatives also. So what you're looking at here is to say that f is a function of x, y, z is not the same as saying f as a function of x, partial f by partial x, y, z. These two functions will be very different, right? And you know that this first type of functions are much easier to deal with. The second type of functions will probably be very, very complicated, right? So this one, the Euler equation on its own involves some partial derivatives. So you need to know fundamental equations. You need to know the equations of state. And indeed, this also shows you that if you knew only two of these, you would be in trouble, right? One partial derivative would be missing. So you need to know t as a function of SVN. Okay? Now, and I will show you what goes wrong if you knew only two of three. So what would go wrong if we knew only two of the three equation of state, or even fewer, only one? What would go wrong? In order to do this, we will go back to our Euler equation and start working from there. So equation 9a, Euler equation says E is equal to Ts minus PV plus mu n. Okay. This derivation itself was kind of magical, for lack of a better word, where we introduced the extensive property, we differentiated it, and then we said lambda is equal to 1. Now we are going to do another derivation, which is also kind of, and I think you have seen it in the homework. It's very similar to that. So let's differentiate both sides. What do we get? dE is equal to TdS plus SDT minus PdV minus VdP minus mu dN minus nd mu, right? There are three terms, and I differentiated all three of them, so I get 6 different things. But we know something else about dE. Anyone remembers the integrated first and second law of thermodynamics? TdS minus PdV plus mu dN, right? Do we have to worry about putting P external or anything like this over here? Are you sure? Nope. This is always true, because this is for the system. This is not for a process. That's the subtle thing. What you are talking about is when we write down dE is equal to delta Q minus P external dV and things like that, right? There, that's true. And we were able to compare these two, and I will keep, so like I said, thermo is not really that many things. It's just a few things which are, it takes time to really get those ideas to become very familiar with you. So this is P is equal to P system. We are not talking about whether this is the same as the environment's pressure or not. We are just talking about pressure of the system. We are talking about a state variable, the pressure, okay? So we have these two equations. Both of them are talking about dE. The second one has 3 terms. The first one has 6 terms. So what's the natural thing to do? What do you think, Sophia? Subtract, right? The left side is the same, the right side has. So if we subtract, what will happen? dE and dE will go away, right? TdS and TdS will go away. Minus PdV and minus PdV will go away. And Oh, I had a sign error here. Sorry about that. Our life would have been plus mu dn and mu dn will go away. So we will be left with three things. We will be left with 0 on the left side equal to s dt minus v dp plus n d mu, right? Therefore, 0 is equal to s dt minus v dp plus n d mu. Okay. Let's just focus on a one component system and define a molar entropy. S, small s, is equal to capital S by n, and molar volume, small v, is equal to capital V by n, and divide both sides by n, right? Then what will we have? 0 is equal to small s dt minus small v dp plus d mu, or d mu is equal to s dt minus v dp. This, which I'm going to call equation number 10, is known as Gibbs-Duhem equation. What is this equation physically telling us? Physically, this equation is telling us, huh? Yeah, sure.
What happens if there are multiple components?
It will look like this. Of course, you can't play the divide by n game. You have to, then when you divide by n, it will look like 0 is equal to s dt minus v dp plus mole fraction x1 d mu1 plus mole fraction x2 d mu2, things like that. Okay. Who is the one who really wanted second homework on Slack? There was one student who was like, where is the second homework last weekend on Slack? Kate, okay. So you want more components. I remember both of you. Special problems for both of you. Trust me, the ideas remain the same. Thermodynamics for multi-component system, just the math becomes a bit clumsy. If you get the ideas here, and in reality, you will probably never have a single component system. You will always have a multi-component system, right? But the math does not really, the physics does not change. Yeah, go ahead.
So we found this only knowing two equations of state, and you said this was going wrong. How's this equation wrong?
This is not wrong. This is fully correct. I have not shown yet that what goes wrong with that. We are getting there. So the first I want to make a physical picture about this. What is this telling us? This is telling us that if you have a one component system, okay, can you change the temperature and pressure and chemical potential independently and still stay at equilibrium? You cannot. This is kind of amazing. This is not obvious, right? This equation is telling you, if you're willing to go out of equilibrium, then you can do whatever you want, okay, no problem. But if you change the temperature of a system, if you change the pressure of a system, and you knew the molar entropy and you knew the molar volume, you should be able to calculate the change in chemical potential of the system. And similarly, if you change the chemical potential and change the chemical and the temperature, you should be able to calculate the change in pressure. Okay, go ahead.
In this case, I should ask out loud the question I already posed to you on slide. How can we derive the equation of state from the fundamental equation if we require to freeze two other variables to get partial derivatives if they are physically interconnected to each other?
I don't see the problem in that. Why is there a problem here? In order to derive this, it's all about slow changes, right?
But I cannot, for example, fix S and yeah, I think
You can.
I can.
Believe in yourself. Okay, you can. You're underestimating your abilities. You can. You just have to design an adiabatic process in order to do that. It depends on the process, right? If you want to work with constant S, do it adiabatically. Okay, so this Gibbs Duhem equation is one of those equations that in physical chemistry shows up, and you think it's an equation with a funky derivation and no use, but it's actually quite profound. Yeah, one moment, Patrick. So let me write down what I just said. So Gibbs Duhem equation says that for a one component system, mu T P cannot be changed independently. I want to make one point, then I'll come to you. So in other words, for any generic system, the number of variables you can change independently is also known as the degrees of freedom. Okay, so if one component system, how many degrees of freedom do we have? 2, because the third one is connected. Out of mu, T, and P, only 2 can be changed. Number of degrees of freedom is equal to 2. If we had a 2-component system, then you can reason through this more general form of the Gibbs Duhem equation, and you will have 3 degrees of freedom. If you have a R component system, you will have R plus 1 degrees of freedom. Yeah, Patrick, go ahead.
Is the sign wrong on 10? When you subtract it over the d mu?
Oh, yeah. Now it's correct, right?
Also, where does the assumption, you said out of equilibrium, we can do whatever we want. Where does that come?
Oh, if we were not in equilibrium, our whole ground on which we were standing would fall apart.
Okay.
There is no E is equal to E of NVS. The fundamental equation is no longer followed if you're out of equilibrium.
Okay, so it's
Just everything, both of Callan's postulates are about equilibrium, right? If you're out of equilibrium, just goes away. You have nothing to play with. It's over. Okay, so okay.
yeah.
So what's okay? Okay, I'll wait. Tell me.
Wait, what's the difference? So what's the difference between irreversible and out of equilibrium?
Irreversible means you're during the process you were out of equilibrium. Irreversible process means you do whatever and then you get to the final state. It's up to you whether you decide to reach equilibrium or not. When irreversible means, the definition of an irreversible process is a process which, when being carried out, you are either mechanically, thermally, or chemical potentially out of equilibrium, or all three. That's the definition. Okay, when you're pulling a piston very slowly, the pressure inside is always the same as pressure external. When you're heating the system very slowly, it's always the same, right? It's basically, if I take you and put you out, then you're out of equilibrium, right? But if I gradually open the window, you're heating up while staying in equilibrium. Okay, so an irreversible process is one where you allow yourself to go out of equilibrium in one or more ways. At the end of the irreversible process, if you wait the system, if you allow the system to wait long enough, it will reach equilibrium in the end. As we know, that was the starting point. Okay, so we have still not shown what exactly goes wrong if we knew only 2 of the 3 equations of state. I mean, we kind of see it intuitively, but the Gibbs Duhem allows us to do it more carefully. So let's remember our equation 10. So let's keep in mind, and let's make sure I don't make a sign error this time. D mu is equal to minus S dt minus V plus VdP, right? Yeah, that's correct. From my notes, that's right. So now, if we knew two EOS, two of the equation of state, let's say we knew P as a function of SVN and T as a function of SVN, and we want to derive fundamental equation of, we want to derive the fundamental equation. So if you look at our Euler equation now, which says E is equal to TS minus PV plus mu n, we can put the pressure term over here. We can put the temperature term over here, but we are left with mu. We don't know mu. But Gibbs-Duhem shows us maybe we do know mu, right? Maybe we can solve the problem. But then something will happen. In principle, we could now take d mu, we could calculate d mu by looking at minus s dt plus v dp, right? Because we know P, we know T. But when we do this and we use this to calculate mu, it will be mu as a function of SVN plus an undetermined constant, right? Because you don't know mu as a function of T and P. You know d mu as a function of dt and dp. So if you know two of the equations of state and you try to calculate the third one, you will always be left with one coefficient. Okay, so then when you put it back over here, you will have a undetermined coefficient dangling, which you never know. And this is exactly our incomplete information. Okay, so we need to know all three equations of state, then Euler equation does everything for us. If we knew two equations of state, Gibbs-Duhem helps us. It shows us a way, but we will have to perform some experiment. We will have to set some, for example, we could use quantum mechanics and say, well, I know something about the ground state of a system, and I will use that to set the minimum value, right? I could start with that, but on its own, we are missing something. The problem is even worse if you knew only one equation of state. And so we saw Gibbs-Duhem. That is not the only form of Gibbs-Duhem. Equation 10 is Gibbs-Duhem from energy representation, right? Our starting point was E is equal to E of SVN. We can also show where V is equal to U in homework number 2, that you can also derive Gibbs-Duhem in entropy representation. This, I think, is the last problem in the second homework. The final result is given there. I'll write it down here. And that will look like E multiplied by D of 1 over T. And 1 over T shows up a lot in physical chemistry and physics, right? That's why we call it inverse temperature. Oftentimes, it's natural to think about 1 over T. Plus V D of P over T minus, and I will just write down the full form for a multi-component system, Nj d mu j by T is equal to 0. So this is Gibbs-Duhem in entropy representation, which is, we are going to call equation number 11. Any questions about this? Okay, so what did we see so far? We saw knowing the fundamental equation takes us to the three equations of state. All we need to do is to differentiate. Knowing the three equations of state takes us to the fundamental equation. How? Euler equation. E is equal to Ts minus PV, right? We put it there and we get everything. Knowing two equations of state does not take us to the fundamental equation. It takes us close to the fundamental. Let me write it down. Recap. Fundamental equation gives us all three equations of state. Okay, simply by how? By differentiation. 3 equation of state gives us fundamental equation. How? Through Euler's equation. 1 or 2 equation of state, we are in trouble. It will give us fundamental equation plus unknown coefficients, unknown constants. And how would we do that? We would do that using Gibbs to Hem equation. Okay, so this is a summary of what we did so far. This is a way to manipulate things. Now,
What's the last thing you've written?
Gibbs to Hem unknown constants. That looks like a
Or
score.
two equations. No, the leftmost thing, right?
This?
Yeah, yeah.
1 or 2 EOS gives fundamental equation plus unknown constants. So, why is all this important? Why should we care about all this math and partial derivatives? Anyone has an idea? You have to take this course. That's one reason. But apart from that, why should you care about this? Does this all have any practical use? What can you think of?
Steam engines.
Steam engines. Do you drive a steam engine? When did you last drive a steam engine? Be practical. Well, even modern day engines, right? In any engine, any airplane, you're using a material, right? You design a material, you test it at a certain. Every time I sit in an airplane, and I sit a lot in airplanes, I just seem mesmerized. I feel mesmerized because outside the temperature is like minus 60 degrees Celsius, right? And the thing works. It's kind of crazy, right? I mean, try writing a computer program and give it to someone else, it will fail. It will fail. That's what happens in my group. Everything works for one of my students. When someone else tries it, it's like, so like Patrick is doing rotation with me and he's trying a code from some other student. And every time it works, it's like, wow, it really works, you know? It's very hard to get things to work in a condition in which they were not tested or designed, right? So these equations are very useful because they allow you to think about one property, how it will change with respect to other property, right? So for example, the fundamental equation, one of the things people do, and there is to do computer simulations or experiments to actually calculate the 3 different equations of state. This is quite common. You will see this in industry, in academic labs, everywhere, okay? You do some sort of experiment, you do some thermal expansion experiment, you do some calorimetry. There are ways to calculate 3 different equations of state. And that allows you to get the fundamental equation. Once you have the fundamental equation, you can start playing all sorts of games and really calculate everything else of interest, things like the heat capacity, things like the compressibility, which we will be seeing through the course of this semester. So the equation of state contains everything that is thermodynamic. It is hard to calculate directly, right? Because entropy is hard, right? What did I say? Fundamental equation contains everything thermodynamically. It is hard to calculate. Equation of states are easier to calculate, and from that you can go back to fundamental equation. And we will see all this in practice. In fact, we will see it for an ideal gas just in a moment as to how can we go back and forth. This is the simplest gas we can imagine. Before that, any questions about this?
How do you keep track of the chemical potential? Like, what do you do?
Diffusion. I will see how things are moving, the concentration, how it changes, right?
But you only, okay.
Just the concentration. Chemical potential sounds very complicated, but it's actually even simpler than anything else. You just have to count. Okay, so
Yeah, so when we integrate, so when we only have 2 equations, so we integrate the Gibbs to Hem.
yeah.
Could you remind me what the molar entropy and the molar volume are?
They are just total entropy by N.
Yeah, but what are they functions of?
Everything is a function of SVN in what we did.
Mhm.
In your homework, everything will be a function of EVN. We are working in entropy representation, so our variables are always SVN. Okay, so I want to talk a little bit about natural variables. We have seen it when we introduced Callan's second postulate, we said there exists a function S, which is defined for all equilibrium states and which has wonderful mathematical properties, which itself is a function of S and N, V, and E. So in a certain sense, natural variables were already introduced. We did not say it exists as a function of N, V, and temperature, right? So they follow naturally from the postulate, the second law of thermodynamics. Then we showed that this is equivalent to writing down E is a function of SVN. And at this point, we said SVN are natural variables of E. What does this mean? This means that writing E as a function of SVN is thermodynamically complete. Nothing is missing. Why nothing is missing? Because Callan's postulate told us that if you have S as a function of NVE, you know everything that is to be known, right? You know whether a state is adiabatically accessible from other state or not. You just compare their S values. If S is higher, you know you can move in one direction. If S is lower, you know you can move in another direction. Instead of S as a function of NVE, if you looked at E as a function of SVN, it is still thermodynamically complete. You have not lost anything. So here is a question for you. Are the following equivalent? We have E as a function of SVN. And we can calculate, if that is given, we can calculate T, which is partial E by partial S at constant NV. And this will give us T as a function of SVN. And from both of these equations, which is E as a function of SVN and T as a function of SVN, we can eliminate S. Okay, let's eliminate S to get E as a function of TVN. Is this also a fundamental equation? Why or why not? You're nodding your head. Why not?
I don't think it is.
Why?
Because if we were going to get DE, it would not be D, we would not have partial T in there, we would still have partial S.
Right. Correct. So what I wrote this down as if it looks complete, but what really we have written over here is E as a function of partial E by partial S at constant NV, comma N, comma V. This is a partial differential equation. Anytime you have a derivative in a fundamental equation, it means it's true only up to a constant, right? Therefore, TVN are not natural variables for E because something is missing. You have a partial derivative. Go ahead.
So when we're discussing natural variables, they always come in a set.
Yeah. But that's the way Callan decided it. Okay, any questions about this? This is all a bit abstract, and the whole point of the midterm, the second midterm, the first midterm is it's basically going to be like a longer homework, slightly harder questions that you cannot discuss with each other, but you can open your notes, you can open internet, you can open whatever book you want. The whole idea is that you take time to go through these concepts and solve the problems and become familiar with them. Okay, that's why I'm giving it relatively early, because if we lose each other at this point, then we are doomed for the rest of the semester. Okay, it's just going to be a sufferfest. What's the point in that? Okay. So let's look at an example which will hopefully demystify some of this as to how do we manipulate things. Okay. And in chemistry, the simplest example is the ideal gas, right? Example for all of this. So my question to you is, what is a fundamental equation for an ideal gas? Is there anyone here who has never heard the word ideal gas or never studied it? You can raise your hand. Maybe you're a mathematician. No, I had a student, like I keep saying, who was like, I don't know ideal gas. So, okay, I don't think anyone is a mathematician here, right? So you have all read the ideal gas at some point. Does anyone know what is the fundamental equation for an ideal gas? I know what you want to say. I know what you want to say. So PV is equal to nRT is an equation of state. Any other attempt? And I would like you to attempt because that's where we will start from. What else? What other equation have you seen for an ideal gas? N by kBT, so equipartition, right? In an ideal gas, everything is moving independently of each other, right? Nothing talks to each other. So we can say the energy of an ideal gas is going to be 3/2 nRT, right? kVr, it's all the same. Right? Depends on how you're counting n, number of moles or number of atoms. So these two are equations of state. Do they look like equation of state? We just said equation of state was T as a function of something, something, right? So let's change it just a little bit, and then you will see why this is equation of state. So this is what you know in chemistry as ideal gas law, and this is equipartition. So why do I say this is equation of state? Because if you think about this one, this gives us 1/T is equal to 1/T is equal to 3/2 nR/E. Or we have just obtained T as a function of n comma E, right? Similarly, this one gives us P/T is equal to R n/V, right? This again gives us P as a function of NVE. Why? Because this is a function of NV, right? And we just obtained T as a function of NE, right? So you can bring T over here and then it becomes joint a function of NVE. So these are examples of equations of state. The ideal gas law is our first example of an equation of state. Important question. What representation are we working with? There are only two choices. And if I say, in energy, that leaves only one. Why?
This is a function of E.
The variable, you have to look at the variable, right? So if NVE are the variables that we are looking at, then it is an entropy representation. We are working in entropy representation. So the question now is, can we find S as a function of NVE? This is something you might have done in your undergrad, but most likely not. It seems almost hopeless. You have the ideal gas law, and you have the equipartition theorem. How do you get the entropy out of that? It seems bizarrely disconnected, right? Any ideas how we might proceed? Not if you have read the book. I mean, if you have, that's good. This is where Euler's theorem will come into use, Euler's equation, right? Euler's equation gave us any relation exactly for things like this, E is equal to Ts minus PV. So we'll use that and see how it works. Before that, let's do one change. Let's introduce, do I need to do that? Yeah, let's introduce molar energy, because we will restrict to one component system. So wide angle capital N. Molar energy, E is equal to capital E by capital N. Molar volume, V is equal to capital V by capital N. With this, we can write down that 1 by T, this thing, 1 by T is equal to 3 by 2 multiplied by R by E, right? Let's call this equation number 12a. Where did the small e come from? The small e is this thing, capital E by capital N. And P by T is going to be R multiplied by molar volume. R multiplied by inverse of molar volume. P by T is equal to R by small v. Let's call this equation 12b. Okay, it's nothing profound, just a change of variables, just a substitution to make things simple. I will write these two equations on the next page again. So we have 1 by T is equal to 3 by 2 R by E, and P by T is equal to R by V. And this is equation 12a, this is equation 12b. What do we want to do? We want to calculate entropy. As per Euler equation, entropy is going to be E by T plus P by T multiplied by volume minus mu by T multiplied by N. So notice that in Euler equation, we already know this part. And so what, and again, before we go further, we already know entropy. So why do we care? Why is this not the fundamental equation? This is not the fundamental equation because we seek S as a function of NVE, right? So we have to get rid of this 1 over temperature here. We have to get rid of P over temperature here. And we have to get rid of minus mu over temperature here. So let's try with what we have and see how far can we make. So if we use 12a and 12b in above, use 12a and 12b, what will we get? We will get S is equal to, and let's go to the molar representation. So if we divide everything by capital N, we are looking at S is equal to E by T plus pressure by temperature multiplied by volume minus mu by T, right? We have divided by N. So let's see how far does equation 12a and 12b take us. We'll get S is equal to E multiplied by 3R by 2E plus R by V multiplied by V minus mu by T. So something kind of nice happens. In the first one, the E and E cancel. In the second one, V and V cancel. We are almost starting to see some sort of constant entropy for an ideal gas. But there is a problem. This one, we don't know what is mu, right? Why don't we know mu? Because we have only two equations of state. We don't have the equation of state for the chemical potential for an ideal gas. So what can we do now? How should we proceed further? We know Gibbs-Duhem equation, right? Gibbs-Duhem equation connects the change in chemical potential with change in. So to save us, comes to help Gibbs-Duhem equation. What does Gibbs-Duhem equation say? And specifically, we are going to use Gibbs-Duhem equation in this entropy representation. Where did it go? Equation number 11, Gibbs-Duhem in entropy representation. I want to stop here because we have covered a lot. I want you to think about, this is a good point to go and finish that third problem from the homework. Just get it done. And it will be very useful if you do that. I know you probably didn't want to do it until the weekend because we all like to postpone things till the last moment, but do that. It will be helpful next class. Okay, we will use that to derive a very interesting relation. Next time we will show something that you have probably not seen before, that the entropy of an ideal gas is given by N by N naught S naught. These are all constants, plus NR multiplied by log of E by E naught to the power 3 by 2, V by V naught multiplied by N naught to the power 5 by 2. Has anyone seen this equation before? Yeah, this is the Sackur something something equation. Sackur what? Tetrode. Yeah, it shows up in physics and chemistry, but we will derive this. And again, notice it will have some undetermined coefficients. Why? Because we knew only two equations of state.
It's like the-
Huh?
It's NR, is it just NR?
Yeah, this one.
Yes.
Yeah, NR. But don't, this will happen next time. Okay, so don't worry about this part. What I would really like you to do is to go and finish the third problem of the second homework, so you're ready. That's what we will start with. That's the relation we will use next time, and then we will start thinking about the concavity of entropy. For example, by which what I mean is we talked about the partial derivative of entropy with respect to energy. Next time we will start thinking about the double derivative of entropy, and that will be our foray into things like enthalpy and free energies. And why do free energies matter? Because chemistry, chemical equilibrium, and things like that. So we are just building up step at a time. Okay, and the office hour will be next week, whatever time I announced. I'm going to do it on Zoom because I tried doing it in once my classroom and just became in my office and it became packed. So I will be on Zoom and we will discuss that.